So we're going to be going over question 4 on the practice midterm, which had to do with optimization and linear/integer programming. So for part A, we're given the following minimization problem, and we want to select the points that are in the feasible region. So we're given the formulation of the problem, which is a linear programming problem in inequality form, as well as the coefficient matrices A and B. We're also given this graph here with one constraint plotted. So we can see that based on our coefficient matrix that the first constraint has been already plotted for us because the line that's being plotted is 2x1 plus x2 is less than or equal to 10. And we haven't shown the region that the inequality covers here, but we know that since the inequality is less than or equal to a positive number, the region that's covered by the line is going to be under the line. Similarly, for the constraint that's plotted here, negative x1 plus x2 is less than or equal to 10. We've plotted the line, and the region that's covered by this inequality is going to be the region below the line. And finally, for this last constraint, x1 minus 5x2 is less than or equal to negative 10. We've plotted the line, and we can see that since the coefficient for b is negative, the region that's covered by this inequality is going to be above the line. So based on that deduction, we can see that the feasible region is going to be the region that's bounded by the 3 different constraints, and it's marked by that big F. And then the points that are in the feasible region are going to be A and B, which are highlighted here. Moving on to part B, which of the following cost vectors would result in the optimization above having an infinite number of solutions? So if we look at our graph here, we can see that the cost vectors need to be pointing away from the constraint lines, but also be perpendicular to the constraint lines, so that all of the points on the constraint line are going to be valid solutions, and they all have the same objective value. So then they're all optimal solutions, which means the LP would have an infinite number of solutions. Based on the vectors given here, we want to see which cost vectors are perpendicular to one of the constraint lines, and those would be valid cost vectors to consider. So if we look at the cost vectors highlighted here, negative 1, 5, negative 2, negative 1, and negative 1, or 1, negative 1, then those are the vectors that are perpendicular to each of the 3 different constraint lines, and pretty much all of the points on the constraint line are going to be minimizing the cost. We can see those cost vectors being plotted here. And as you can see, they are perpendicular from each of the constraint lines. And they're also facing inward because we want to minimize all of the points that are on the constraint line so that they can be optimal objective points. So now we're going to move on to part C. Given the optimization formulation below, we're going to match the feasible region shapes on the next slide, which are labeled A through H, to the A matrix and B vector that could have created that feasible region. So some things to remember include that the feasible region is going to be in the interior of each shape. The x1 axis is horizontal and the x2 axis is vertical, and all A sub I, j and B sub I are positive values and are not necessarily the same values for each shape. So this first matrix in part I has A populated with some values and some are zeros, and then B is populated with some constants as well. So in this case, it's important to remember that when, for example, the x1 dimension has a coefficient of 0, then that means your line is going to be horizontal because it's just going to be x2 is less than or equal to something. And similarly, if your x2 dimension coefficient is 0, then that means your line is going to be vertical because the line is just going to be x1 is less than or equal to something. And since all of our constraints in this first problem have only one dimension coefficient and the other one is 0, then that means there's going to be 2 horizontal lines and 2 perfectly vertical lines. And the only region that satisfies that constraint is going to be region E. Moving on to part 2. In this case, we have A has some coefficients and B also has some coefficients. So let's take a look at some of the properties of these constraints that are given in both of these matrices. So the first constraint that is in the first row of A and B we can observe that the x1 intercept is going to be positive. And the way to figure that out is we can just set x2 to be 0 and see what the sign is going to be for the resulting x1. So here, if we set x2 to 0, then our x1 is just going to be equal to b1 divided by a1 comma 1. And since both of those values have positive signs, that means our x1 is also going to be positive in that case. We can also calculate the x2 intercept in that same manner. In that case, we find that the x2 intercept is negative. And finally, we also observe that our b is going to be positive. So now looking at the other three constraints, which have the same signs for the coefficients, we can see that the x1 intercept will be positive because when we set x2 to 0 and we calculate it, let's say for the second constraint, our x1 is going to be negative b2 divided by negative a2 comma 1. And since the negatives cancel out, that means our x1 is going to be positive. We can also find that our x2 is negative and our b value is negative. So if we look at a sample graph for each of these constraint scenarios, we can see the following. So for this blue graph here, we can see that the x2 intercept is negative, while the x1 intercept is positive. Also, we see that our b is positive. So that translates to the fact that the inequality coverage is going to be above the line. We can also see phenomenons going on with this red graph here. It has the same formulation where the x1 intercept is positive and the x2 intercept is negative. But in this case, since the b value is negative, you should be able to see that the coverage of the inequality is going to be under the line. So if we try to map these constraints to a particular region here in our options, then that pretty much means that we want to see a region where we have a line that has a positive x-intercept, x1, and a negative x2 intercept, and has the coverage being above the line. And then there should be three different lines that have the x-intercept, x1 intercept that's positive, the x2 intercept is negative, and the coverage being under the line. So in terms of a sample region that has all of these constraints, we can see that looking at region C, if we think of the blue line as being mapping to something like this, so if this line represented the first constraint, then that means that the coverage above this blue line would be in the feasible region, which is what we want because the interior of the region is going to be feasible. We can also see that for each of the three red lines here would map to any of these three constraints that are given in the second, third, and fourth rows of our A and B matrices. And since the coverage of those constraints is going to be below the line, we can see that's also the case for part C, where for this line, the coverage is going to be below the line, and same for these other two constraint lines. And therefore, if we mapped each of these constraints to region C, then that means the feasible region is going to be inside of the boundaries of these four different lines, which means that a possible region for this particular configuration of A and B would be this region C. Now looking at example 3, where we're given this configuration of A and B matrices. So we can also do something similar by observing the properties of this A and B matrix. This is what it would look like. So for the first constraint, we can see that both the x1 and x2 intercepts are going to be positive. And then the b value that's given is also positive. For the second constraint, we can see that the x1 intercept would be negative because if we set x2 to 0, then that means x1 would be equal to b2 divided by a2, negative a2 comma 1, which means that the sign on our x1 intercept will be negative. We can also calculate the x2 intercept, and we'd see that the value is positive. B is also given to be positive. And then finally, for the final two constraints, which have the same configuration of signs, we can also find that x1 is negative, the x1 intercept is negative, and the x2 intercept is positive, and b is also given to be negative. So now we can try mapping these to their corresponding sample graphs. As you can see here, for this first configuration, we find that the x1 intercept is positive, and the x2 intercept is also positive. And since b is positive, if we do some minor calculations or testing of sample values, we can see that the inequality coverage would be below the line. You can also do similar reasonings for this orange graph here and the purple graph here. Now we can try mapping these graphs to the feasible regions. So we want one line where it has a positive x1 intercept and positive x2 intercept, and the coverage is below the line. So that might look like something in part H. So if we look at this line, the green line, it satisfies that criteria where the slope is negative and the coverage of the line is going to be below the line. If we look at the orange lines, since we have two different constraints to satisfy that, we can see that the two orange lines in this corresponding region kind of satisfy that constraint where the slope is positive and the coverage is above the line. And then finally, for this purple line, we can see that this purple line in H satisfies a constraint where the line is having a positive slope and the coverage is below the line. So therefore, we can construct these four constraints into a region that's similar to H. Now looking at this configuration of A and B matrices, we can do the similar analysis for the x1 intercept, the x2 intercept, and the B value. And that can be used to construct the sample graphs here. This is similar to something we saw in the previous part. We're going to have two lines where the slope is positive and coverage is above the line, and then two other lines where the coverage is positive, or the slope is positive, but the coverage is below the line. And that would map to something similar to region F, where there are two lines where the slope is positive, but the coverage is below the line, which is similar to this red region here. And then two lines where the slope is positive, but the coverage is above the line. And so that helps us construct our feasible region. Now moving on to part B, where we're given this configuration of A and B matrices. So in this case, B is always positive. And then we're given four different configurations of the signs for the A values for each constraint. So in terms of the graphs that are generated from each of these constraints, those graphs would look something like this, where we have four different configurations. One is where we have two lines where the slope is negative, but then for the first constraint, the coverage is below the line. For the second constraint, the coverage is above the line. And then we have two other constraints where they have a positive slope, but then for one constraint, the coverage is above the line. And for the second constraint, the coverage is below the line. So we can combine this information and try to see which one of these regions kind of fits the criteria for these four different constraints. And taking a look at each of these regions, we see that region A kind of fits that criteria where each of the lines that are part of this particular region have a matching corresponding constraint, which is represented by one of these graphs here. So then A would be our correct region. And finally, for I guess part 6, we have the given A and B matrices. These map to two different configurations for lines. The first one is where x1 intercept, x2 intercept, and B are all positive. And then the second one is where x1 intercept, x2 intercept are positive, but B is negative. So if we look at the region that this maps to, we can see that there are two lines. Both have negative slope, but one has coverage above the line and one has coverage below the line. So then in region B, we can see that same phenomenon going on for these two lines. They're both having negative slope, but their coverage is going to be above the line because that's where the feasible region is. Whereas for the two green lines in this feasible region B, they have a negative slope as well, but their coverage is going to be below the line because that's where the feasible region is located. And so B would be the answer to this question. So now we're going to go through part D of question 4 over some minimization integer programming problems. So each graph that's going to be on the next problems has 3 constraint boundaries with the feasible region marked with an F. And in addition, the cost vector is shown with the arrow given. So for each problem, we're going to select all the graphs that satisfy the given requirements. So for this first part, we're given the information that X star LP is the LP solution and X star IP is the IP solution. So for this first graph, A, we're going to see that the cost vector is pointing towards the left and down. And then we're given 2 points here, XLP and XIP, with the 3 different boundaries, which represent the constraints. And the feasible region is that bottom region here. So in terms of if this satisfies the constraints or not, we're going to see that the X star LP is indeed a valid solution to this particular problem. But if you tried running branch and bound on this graph, we're going to see that this particular X star IP is not an optimal integer programming solution. So let's go ahead and run branch and bound. So if we, let's say, branched on the X domain first, if we assume that the horizontal axis is X and the vertical axis is Y, then in that case, our branch and bound would lead us to the solution for this right branch here. X is greater than 4. We're going to greater than or equal to 4. Sorry, I think that's a typo. But the corresponding solution that's returned with this extra constraint would be at this yellow dot. And then let's say we ran branch and bound on that yellow dot. That solution, we added it to the queue and then we popped it off. And then we added, well, the X constraint is an integer, so then we had to branch and bound on the Y constraint. So if we added 2 different constraints, Y is greater than 4, greater than or equal to 4, and Y is less than or equal to 3, then one of the IP solutions that would be returned would be at this yellow dot, which is X star of IP. So this could be potentially a valid IP solution, but keep in mind here that the IP solution that was given to us in the graph was at this point here, which definitely has a larger cost than the point that we found by doing branch and bound, which means that the point given by the graph would not be the optimal IP solution. Therefore, this example is invalid. Okay, so looking at graph B, we're given the LP point at the intersection of 2 of the constraints, the cost vector pointing to the right and down, and the IP solution given at one of the points. But in this case, it's important to observe that the LP solution doesn't really minimize the objective the most that it can, because it's on the right side, but your cost vector is pointing towards the right, which means that the intersection here would definitely have a lower objective value, which means that it would be your optimal LP solution. Okay, so this is graph C. We're given that the LP solution here is at the top of the intersection of these 2 constraints. The feasible region is given in the boundaries of these 3 constraints, and then the cost vector is pointing downwards. So in terms of if we think this is a valid solution or not, we see that this does satisfy the conditions that we have for the definition of LP solutions and IP solutions. So we first observe that X star of LP that's given to us is the topmost intersection. And the top is the, I guess, dimension that we want to minimize the most, because our cost vector is pointing mostly downwards. So then the topmost solution would lead us to the solution that has the minimal objective value in terms of the LP solutions. And then once we perform branch and bound on this example, which I'd leave to you as an exercise, you would see that X star of IP would be an optimal solution that you find via the branch and bound algorithm. Finally, we can look at graph D here. We're given a configuration with the LP and IP points. We can see that this does not satisfy the conditions because our cost vector is pointing towards the right. So then the intersection that would minimize the cost vector the most would be the one that is on the leftmost side, which is this intersection here. And so therefore, the LP point that is given by our graph is the incorrect LP point because it does not minimize the objective value. So now what do you think the branch and bound algorithm will do? We have 4 different choices. It can return X star of LP, it can return X star of IP, it can return infeasible or never return at all. So in these cases where we have a plausible IP solution for each of these graphs, we're guaranteed to say that branch and bound will return X star of IP, and that's because the branch and bound algorithm is complete. Moving on to part 2, X star of LP is given to be the LP solution, and the IP solution is infeasible. So in all of these cases, we want to check to see that there is no possible IP solution that can be found while doing branch and bound on the given LP objective point. So first looking at graph A, we're given the cost vector pointing to the left, the X star of LP being the rightmost intersection point of the constraints. And then the feasible region is given as that triangle. So this graph does satisfy the conditions for the given conditions in the problem, because the minimum objective value for the linear programming problem is going to be the rightmost intersection point because our cost vector is pointing directly to the left. And then if we observe our feasible region, there are no integer valued points that are going to be viable solutions, because whenever the X value is an integer, the Y value is not an integer, and then whenever the Y value is an integer, the X value is not an integer. Moving on to graph B, where we're given the cost vector and the LP point, we can say this does satisfy the conditions. This is because the cost vector is pointing mostly downwards, so then our LP point would be the topmost intersection point, which this X star of LP is. And then if we look at the feasible region F, there is no Y value where this particular solution for this particular feasible region, because the Y values are bounded. So then whenever we branch on the Y value, for both branches, we would return an infeasible solution. Okay, moving on to graph C. In this case, we're given the cost vector and the LP point and the feasible region. So in this case, we can see that this will not satisfy the conditions. And this is because we can observe the feasible region and see that there is a valid integer point that would be a valid point for this particular linear programming problem or integer programming problem. And that could be a solution that's returned. So the IP solution is not infeasible, and branch and bound would definitely find this solution while running the algorithm. And finally, looking at graph D, we're given the feasible region with the cost vector and the LP point. So in this case, this does not satisfy the conditions because the LP point that's given is not the leftmost point, even though our cost vector is pointing to the right. And so in order to minimize the objective, we would select the leftmost point, which means that this LP solution is not optimal. So now moving on to what the branch and bound algorithm will do in these particular cases. When the LP solution is given, but the IP solution is infeasible, then our branch and bound algorithm will return infeasible. And that's because it was unable to find a solution to the integer programming problem for that particular set of constraints. Finally, looking at part 3, in this case, the minimum objective for the LP problem would be negative infinity, and the IP solution is infeasible. So if we look at graph A, we can see our feasible region is given in that top region, between the two pink lines and above the blue line. But our cost vector is pointing upwards. So in order to minimize the objective, we would select points on that blue line because they would minimize the objective value of this particular cost vector. But in this case, our graph does not satisfy the conditions because we wanted the condition that our objective value is negative infinity. But since the minimum objective points in this case are bounded by that blue line, then our objective value will not be negative infinity. Rather, it will be some particular number value. Moving on to graph B, it's similar to graph A, except the feasible region is going to be that bottom region between the two pink lines. This graph does satisfy the condition, and this is because now if we're trying to calculate our objective value for the minimum point, in order to minimize this particular cost vector, we're going to keep going down and select the point at the very bottom of this graph, which is going to be at negative infinity in terms of the y value. And then, so for that, if we evaluated the objective value for that particular point, that would also be negative infinity. And this is because there's no constraint that bounds the lower part of the feasible region. And then if we took a look at the integer programming solution, in this case, we can't find an integer valued solution because A, we're finding points at negative infinity in terms of the y values. We could try branching on that, but that wouldn't give us an integer valued solution. And then also in terms of just the x values, since the pink constraint lines are not covering any integer valued x values, then in that case, we can never find an integer valued solution because there are no feasible points that are integer valued within the boundaries of the constraints. Now looking at part C, we're given feasible region F and the cost vector pointing downward and to the right. But in this case, this is similar to part A because we have this pink constraint line that's diagonal, that's I guess bounding the feasible region. So if we try to minimize the objective value, then our minimum objective value would be at that point of intersection and the cost, corresponding cost for that particular point. And since that intersection is real valued, that means the minimum objective value for LP cannot be negative infinity for this problem. Finally, for graph D, we're given the same setup, except the cost vector is pointing up and to the left. So for this particular case, we can definitely minimize to negative infinity because we can keep going in the right direction in order to minimize because the cost vector is pointing up and to the left. And therefore, since we can infinitely go in the right direction because it's unbounded, and no constraint bounds the right part of the feasible region, that would lead us to a point where the x value is equal to infinity, which would lead our corresponding cost to be negative infinity. And then this is for the IP solution being infeasible, it is similar reasoning to graph B because we cannot find an integer valued solution in the feasible region. Finally, for this case, what will the branch and bound algorithm do? We have different options: return negative infinity, return infeasible, never return, or throw an error. So for this problem, we have multiple different cases that could occur because the essential thing is that we don't know what would exactly happen and how our algorithm would behave when it sees negative infinity. So we kind of have to cover all cases for all different algorithms. So in the first case where the algorithm could return infeasible, that might be because it branches on the non-infinite coordinate of the solution point. So remember, for example, we saw in graph D that the two pink lines that are the constraining the feasible region didn't have any values for y that were integer valued. So if we branched upon that y coordinate, then in that case, we would never find a solution because both branches would return infeasible. The second case is that if the algorithm never returned, in that case, we would pretty much see infinity as part of the LP solution and infinitely branch upon that infinity because we can never really add a constraint that helps bound that unbounded region in order to limit the solutions. So we just keep branching and bounding upon infinity, and that would be endless. And finally, the algorithm might be smart and throw an error when it sees infinity and say that's an invalid solution value so that it doesn't end up branching and bounding infinite. And this is largely dependent on how it's implemented, as I said earlier. And since you can't really assume the behavior of the algorithm, you have to consider all cases. So that's it for question 4. I know it was definitely a little long, but there were a lot of different good topics that this question covered in terms of linear and integer programming. And I'd say those are definitely important concepts to keep in mind.